Hi, in this video, we're going to take a look at other ways to evaluate model quality besides accuracy when we're doing logistic regression. All right, so in particular, this is going to be important when I have an imbalanced data set. So let's say that I'm doing a project with like a rare disease, and 99.9% of my observations do not have the disease, and that fraction of a percent do. All right, well, in that situation, if I just declare nobody has the disease as my model, then what would happen is I would have 99.9% accuracy just like that. But you know what? That's not a useful model. I've completely missed the cases that we're actually interested in. And so this example is to highlight the fact that regular old accuracy isn't good enough when I have an imbalanced out. Now, if it was 50-50, disease, no disease, accuracy would be perfectly good, wonderful, and that's what I would use. But here we want to, tune things to handle the more nuance with this data set. All right, so let's dig into it. All right, so for this, once again, I'm going to set up my workspace where I'm going to limit the number of digits printed, avoid scientific notation, avoid warnings being printed, make sure I don't have any gunk in my workspace, and I like piping, so we're going to load the Magritter package. Okay, so let's go ahead and load our data sets here. And this is from the imbalance package. And I'm just going to go through and get the yeast 4 data set. That's the one that we're going to end up using. And let's take a look at what we've got. So we've got some predictor variables to work with. Now, I don't know anything about this data set. I honestly don't care because what I want to do, I want to demonstrate the idea of imbalanced data. So check out the class. Here we have over 1,400 are negative, while only 51 are positive. Okay, so we have a single-digit percentage of positive cases. So I have a very imbalanced data set. All right, so let's see what we can do with this. All right, so I'm gonna go through, do a little bit of data prep. Gonna go ahead and take the LR, and I'm gonna change this over to dummy variable format, because there's right now this is a factor, and so I'm gonna go through and sample on this to use a sample function to partition my data into train and to test. I'm going to change my target variable into a factor. And then I'm going to sort my data. It's a small data set. I'm going to sort it by the target variable so that this might help me figure out what's going on, detect patterns as I work through my project. Now here, I'm going to go through and get all the other columns to be predictor variables. So I'm saying, hey, these are my predictor variables. This is something I like to do at work, is I take all the variables that I want for predictors and I put them into a list or a vector. Vector if I'm in R, a list if I'm using Python. I did a list in Python today, by the way. Now let's go ahead and do my pre-processing. And so here, I'm just going to do this in the laziest way possible. I'm just going to go ahead and drop this into the pre-process function in caret. And this data set doesn't have any missing values, so that's not an issue. I'm going to go ahead and just says first run, try everything. And I'm just going to go through and just do some transformations of Box-Cox, Yo-Johnson, or exponential. What's going to happen is the pre-process function will try Box-Cox if it can. If that doesn't work out, it'll go to Yo-Johnson. If that doesn't work out, it'll go to the exponential transform. And that is the order that I would prefer. Just from experience, I find that the Box-Cox transformation is the best one to use, and Yo-Johnson is a good one to use if if Box-Cox is not applicable because of non-positive values. And then to be able to actually modify my data set using the pre-process function, I actually have to run predict on the object. So I'm going to run predict on the pre-process function. So what this is a function that will take data and apply the Box-Cox, Yo-Johnson, or exponential transformations as needed on them. And then I just specify the data to be transformed. All right, so now this version of the data is not the original columns, it's the transformed version of the columns. All right, so let's go ahead and go through and visualize our data. So I have a better idea of what's going on. And so I'm going to group by class. I'm going to get some counts. And then I want to take a look at the percentages. And so let's do a bar plot on this. All right, so we can see that 97% of the observations are negative, 3% are positive. So I've got some imbalanced data going on. So now let's go ahead and start visualizing our individual predictor variables by the target variable to see if we can see which predictor variables will be highly useful. Remember that this is the post-transformed version of the data. All right, so what I want to see, if I see the lumps of dots in very different vertical positions, then that's an indication that it's going to be a stronger predictor variable. If it looks like the central tendency and the variance are the same for both groups of dots, then that's an indication that the predictor variable is not going to be useful for my purpose. And so here, since we see that this clump is higher up, maybe MCG will be useful. Let's keep on going. Now here, this looks like GHV will be less useful than MCG, just because this is just kind of evenly spread out. I don't see like a distinction in the horizontal or in the vertical position. And now pretty much the same conclusion for ALM. That this is on the lower side, but then there's a good portion here also. So there might be some utility here, but not as much as I would like. Yeah, this looks pretty evenly distributed. I'm expecting MIT to not be useful as I fit models. And here now ERL, this might be useful because we can see that we've got some points here. Now, there's definitely going to be some overlapping points. So it like here we've got definitely a bunch of points that are positive that are getting overlapped with the negatives. Yeah, we can't even see the positive cases on this one at all. And you can see that we have our points here. Every single time I have the same number of red points. And so, the teal are, just obscuring what's going on. But, just emphasizing how much we have imbalanced data. All right. And so MCG looks like it's, probably the most promising one. All right. Looks like my code printed these out twice. Let's just scroll past that. All right, so with imbalanced data, the constant model is highly accurate, but it's not really a model. All right, so for imbalanced data, if we create a model that always predicts negative, regardless of what the independent variables give us, we end up having pretty good accuracy. So let's check this out. If I just say every single time, negative, now I'm going to look at the data, now I'm going to look at the observation, I'm just going to go, you know what, it's negative. I'm going to pull off nearly a 97% accuracy like that, which is nice. We didn't have to do a lot of work, right? Easy peasy, lemon squeezy. But that's not really a model, right? Kind of defeats the whole purpose of doing statistics. Like, why would my stakeholders pay me? Why would my boss pay me to do that? There's no reason for that. So let's go ahead and start working on this a little bit deeper. So let's do a confusion matrix. So I'm going to go ahead and do a confusion matrix with the all negative model. So the constant model where I just say everything is negative. I don't have any positive cases. It's a stupid model, but just as a reference point, we're going to start here. It's 97% accurate, which means that I've got pretty darn good accuracy. But I'm just going to run with it so that we can see what's going on with some metrics, and then we're going to shift directions and try something else. So a confusion matrix is a contingency table of our predicted classes and our observed classes. Some software puts the predicted classes in the rows, observed in the columns. Other software put the observed columns in the rows, predicted in the columns. Be ready for the difference. I've had some people get like really butthurt over this one. It's not a big deal. I mean, just take the transpose. It's not, just do whatever your audience is more comfortable with. And when we go through and do our train validation test splits, we'll actually do confusion matrices for each of these. And this will lead to statistics for our training data, validation data, and our test data. The constant model is simple. And so just to make things easier to understand, we're going to look at the constant model. And so here I'm just saying negative every single time. And now this is a factor with two levels of positive and negative. I just have 0 occurrences of positive. So let's take a look at the resulting table. All right, so here, every single time I'm saying negative. So every time the actual value was negative, I nailed it. But every time that it was positive, I made a mistake. So every positive case, I'm wrong. My accuracy is 97% accurate. Wow, I mean, it's really nice, not much work. Here I've got a strong confidence interval. My no information rate is 0.977. My p-value is pretty good. So here we failed to reject that our accuracy is equal or less than the no information rate. My kappa is 0, which is bad. My p-value for McNemar's test is very, very low. That's because it's a very lopsided rows. Now check out the sensitivity. I have a sensitivity of 0, worst possible sensitivity I could get, which I'll define sensitivity in a moment. My sensitivity is 0. So this is showing me that by this metric, I have a terrible model. Now my specificity is perfect, because I have such a lopsided model. My positive predictive value can't even be computed. My negative predictive value is once again 97. My prevalence is super, super low. My detection rate is super low. My detection prevalence is low. My balanced accuracy is a half. And so the balanced accuracy is a better measurement that we can see that, well, it just isn't figuring this stuff out right. And so what you should see here when I look through this, either I'm nailing it or I'm completely falling on my face. Very extreme results because I have very extreme data and very extreme model of all negative. So now let's think about trying to interpret what these metrics are. Okay, so if I have if I have a positive prediction and the actual value is positive, that's called a true positive. If the prediction is positive, but the value was negative, I made a mistake, it's a false positive. If the prediction is negative, but the true value is positive, I made a mistake, it's a false negative. And if the true value is negative and the actual value is negative, so if prediction is negative, true value is negative, then it's a true negative. All right, so anytime we say true, we got it right. Anytime we say false, we got it wrong. Okay, so sensitivity, this is also called the true positive rate, is a modeled probability of a positive test result conditioned on the individual truly being positive. All right, so here is the calculation. So the true result is positive, so the false positive count plus the false negative count in the denominator, the true positive result in the numerator. That is sensitivity. Now, specificity, called the true negative rate, is the probability of a negative test result conditioned on individual values being truly negative. All right, so if I look at specificity, we have true negative and false positive. So all the cases that are truly negative, that is my denominator. In the numerator, I have the true negatives. That's my specificity. And so sensitivity and specificity, that gives me my true positive rate and my true negative rate. These take into account the size of my data. So this is a more tuned approach, more precise look at accuracy, because when I look at sensitivity, that's accuracy when the actual result was positive. Specificity is accuracy when the actual result was negative. Now, precision, which is also called the positive predicted value, is the fraction of relevant events among the retrieved instances. And so for precision, I take true positive and false positive. So all the times that the model called positive, how often was I right? And then recall, I have true positive and false negative. And you'll notice that this is the same as sensitivity here with true positive and numerator. Now the positive predicted value is all the times that the model called positive in the denominator with true positive in the numerator. And so you know this is the same as precision. So these have like, redundant names. Now, negative predicted value is when the model calls negative, whether it's right or wrong, in the denominator with true negative count in the numerator. And then prevalence is going to be the sum of total cases in the denominator with true positive plus false negative. So this is the prevalence of times that the model calls positive throughout. Now the balanced accuracy, and this is probably the accuracy that you should lean on the most in most cases, is going to be the true positive divided by false positive, true positive with false negative. So all of the positive cases for all the modeled positive cases in the bottom with true positive in the top, all of the modeled negative cases in the denominator with true negative in the top, and then divide by 2. Another way to look at this is that this is the average of sensitivity and specificity. That's our balanced accuracy. All right, so let's go ahead and fit a model. And I'm just going to go through the regular old GLM, and I'm going to set up so that my cutoff is 0.5 because that's my default way of I don't know what else is going on. And let's look at the confusion matrix. All right, so the confusion matrix said positive 10 times, and you can see that half the time it was wrong. Well, that's not very good. It's oh, and I am partitioning over the data set. So as I go through this, I do have my train and my test data sets to work on this. I do my confusion matrix. So here, the first one is going to be my train. And so here we can see half the time on the training set, and the training set's the one that it does better on usually. We half the time when we call positive, it was wrong. And we had a good decent of mistakes when the model called negative. The accuracy is still 0.97. All right. I mean, so overall for accuracy, I did pick up a little bit more sensitivity, but I didn't lose any accuracy in it. My kappa improved, sensitivity improved, specificity went down just a touch, just a touch. Positive predicted value at least can now be computed. Negative predicted value went down just a touch. And we can see that overall we have a better model. But you know what? We can do better than this. Now here is things for my test set. And so we can see that we actually did better when we predicted positive. And so we have, a slightly improved accuracy, and everything is pretty much consistent with my training statistics. This wasn't like this isn't a very complicated model, and I don't have a lot of parameters for my number of observations. So the overfitting is not an issue. I'm pretty far from it, and my training statistic, my test statistics are pretty tight with each other. Now let's do an upsampled model. What I'm going to do, I'm going to sample with replacement the low frequency level until I have a closer to balanced data set. All right, and when I do the upsampling, I'm going to use the carrot package to do this. I'm doing it on my training data. You notice I'm not doing it on the test set. And I'm, once again, I'm setting up the cutoff of 0.5, a good default to start with. I could change that later. And let's go ahead and take a look at how things perform. All right, so now we can see that our accuracy went down overall, but you notice that my balance accuracy shot up. So I have a much better balance accuracy that when I consider what's going on, we're going to get a better result. Now let's take a look at the test set. So here, this is still a huge improvement, even though my balance accuracy decreased. So what's going on here is that I took my training data, I balanced it using upsampling, but I left my test data alone. I didn't, and change things. And what I did was that I, just went ahead and left the default 0.5. I could actually probably improve the threshold cutoff. And you can see that my balance accuracy, which was previously 0.5, is now 0.8. And so this is a huge improvement in what's going on. Sensitivity is 0.73. I'd like to see that higher. Specificity is 0.89. It's close to where I'd be happy. But the balanced accuracy is a huge improvement compared to what I had before. All right, so let's go ahead and recap this. What are the different metrics? So our sensitivity is our true positive rate, where we look at the cases where we called positive in the model and how often were we correct. Specificity, that's our true negative rate. When the model said negative, how often were we correct? Precision is where we have, or actually, let me reword this. Sensitivity is when the true result is positive and we're right. Specificity is when the true result is negative and we're right. Precision is when the model calls positive and we're right. And then accuracy is just how many times we get right overall. Balanced accuracy is the average of sensitivity and specificity. And so using these, we have the ability to take a more nuanced point of view of accuracy instead of that blunt version. Remember, accuracy can be misleading with imbalanced data. If I just go, hey, I have imbalanced data, just say the most common one, I actually pull off a pretty good accuracy with a model that is completely meaningless. Of course, we have to do better. All right. That's all I've got for you. Life is short. Do math.